And this should be the first video, but I already filmed the first one, but let's make it the first one. We will talk about CoCoSim and what does a high level presentation about the tool. So maybe I should bring some slides I did a long time ago. So CoCoSim is an automated analysis and compilation framework for Simulink and state flow. It has been developed first by Onera and then Iowa University and Carnegie Mellon University. Then NASA kept supporting the tool and developed its own version. I will try to go over what is formal verification informally and what is CoCoSim and how we validate the tool and some stuff. I will not go over all the slides, but just the one that I see that very important for anyone that is new to the topic of formal verification. So CoCoSim stands for contract-based compositional verification for flight critical systems. So CoCoSim was developed in a joint project, and many tools have been developed in the same projects as CoCoSim. The famous ones are Kind2, Lustre model checker, Lustre also. C-Horn is for C verification, static analysis. So anyone watching this video is already familiar with Simulink. Simulink is mainly used for control systems, and it's very useful, and it has a lot of rich libraries that makes the development of model-based development very fast. And since they have a lot of fancy and complicated blocks that the user can just use out of the box, it makes the development of models very fast. And it's a hierarchical model, so you can have a subsystem inside a lot of layers. You can have the first layer and the second layer, and you can make things you are very complex control systems, and it's very used in industry. Airbus is using SCADE, a very similar version of Simulink for discrete time. Boeing and American companies are mostly using Simulink for model-based development. So for any system, we start by requirements, high-level requirements, and then we design the requirements in some low-level. Simulink is not that low-level like C code, but Simulink, we can simulate the model, we can execute the requirements, and then we can auto-generate the source code, and that source code can be used later on to be embedded in the hardware. So at NASA Ames, where CoCoSim was, where I developed CoCoSim, we have many other tools that are used for the whole V cycle. So we have FRET for requirement elicitations and formalization tool that can be used in the requirement level. So if you have an English requirement, then you can generate a formal representation of that requirement in CoCoSpec or LTL format, which is just a mathematical, formally defined output, or the semantic. You generate a semantic for that requirement. Then once you have that requirement, maybe you can attach it manually to the Simulink model or automatically, because FRET and CoCoSim are connected. You can attach that requirement to the Simulink model, and you can use CoCoSim, the one I'm presenting now, to formally verify that requirement or that property holds all the time or not, using model checking. So, and then ICOS, once you generate the C code, you can run ICOS to verify runtime properties, like not like CoCoSim, we verify functional properties and functional requirements that talks about how the system should behave. ICOS is trying to verify that the source code that will be embedded in the final hardware is free from runtime errors like integer overflow or null pointers or index outbound index for arrays. So then once you have all these tools running and having verification artifacts, you can use Advocate to make an assurance case for certification purpose. You can make an argument that your software has been validated and well developed and respects all the certification process thing. So these are all the tools we developed in NASA Ames. Why using CoCoSim? So CoCoSim, like in this figure, I show that the introduced errors are are mostly coming from the design and from programming. That most of the errors, but are lately detected in the system testing. So they are introduced in the design level, but they are detected in later on in the testing. And if we want to fix those errors that are later on detected, they cost a lot money-wise. So the cost of correction is very high in the system testing part. So having CoCoSim at the design level, it will help us detect errors early at the at early stages of the development cycle of a product, and then we can fix errors early, and then we can reduce the cost of correction later on. So what is the difference between proving and testing? Because CoCoSim is not testing your software, it's trying to prove that a property is correct for all possible executions. So testing is, as anyone knows, that it's very limited. So we are testing just a very small part of your input space, very tiny parts of the input space. You are just making scenarios, and you try to validate that these case scenarios are that your system behaves well under those scenarios. While proving, we try to prove to reason about the whole input space for any possible execution. So, for example, you have a you have a controller that is developed in Simulink, and you ask, does your controller satisfy some functional requirement? So, what CoCoSim is doing is trying to generate this controller in a formal definition, a formal defined language like Lustre. Since Simulink is not formally defined, we use a formally defined language which the semantic is well defined, and then we have the property in some formal annotation, and we have a model checker that apply model checking techniques that try to prove that your property holds on in all possible execution of your system. And for anyone interested in the topic, you can type model checking in Wikipedia. They explain how does it work and what are the strengths and the weaknesses of this technique. Here I just reference some of the strengths of model checking. It can be used in a wide range of applications, from hardware to software. It can support partial verification, and that's very important because we can try to prove like just components of your system, and also we can try to abstract the components only to prove the high-level properties, and we can do many stuff that we don't need the full implementation of your system to prove properties. And also, it provides diagnostic information, which is the counterexample. So if the model checker is able to find a counterexample where it's like a scenario where your property does not hold, then that's very useful for the developer to debug the system and debug why the controller or the Simulink model is not correct. And most of the time, the model checker will give you like undecided or unknown results. So it's like non-conclusive results. It means that the model checker cannot prove or falsify some property because of the weaknesses of this technique that I will explain in the next slide. So less user expertise is required because these model checkers are automated, which means that you give it your model and your property, and then you run the model checker, and then you have the results. You don't need any expertise to try to prove things by yourself, like theory proving, where you need to add a lot of information about your system to prove things. So usually it requires less user expertise, and also it has increasing interest in industry, from Intel, from hardware companies to software companies as well. So the weaknesses of model checking is it's mainly appropriate and mainly used in logic-intensive or control-intensive applications, because these solvers that we use, the mathematical solvers like Z3 and CVC4 and all these solvers that are used in model checking, they are they have difficult time proving things that are nonlinear or that includes nonlinear arithmetics. So also it verifies a system model. So it verifies that formal representation we gave to the model checker. It doesn't verify the Simulink model itself, because we have a translation from the Simulink model to Lustre. Lustre is a formal synchronous data flow language, and that Lustre is the one that is given to the model checker. So when we have maybe the translation from Simulink to Lustre is not correct, and maybe if we say that the property is safe and it's proven, maybe it's not, because some error in the translation happened. So it's not complete in the sense that you cannot fully trust the results from the model checker if it is safe results. But if you have a counterexample, you can play the counterexample to see if the counterexample holds in the Simulink model. And that's where it's very useful. It suffers from the static space explosion problem, so we have memory and time limitations. So when you are handling very large systems, when you are working with large control systems, model checking have problems with like exploring the state space of that system. From memory point of view of your machine, your laptop or your desktop, to the time problem, exploring in a very limited time. So most of these algorithms are exponentially like they need a lot of time, a lot of memory to prove things. But in order to get rid of these weaknesses, we work in CoCoSim on compositional verification and how we can use abstractions to reduce the state space of the system and to improve the time of the verification and to improve the verification results. So model checking is used everywhere, I think, in any critical system nowadays, like in hardware, avionics, automobile, space, and others. So what is CoCoSim? So this is the CoCoSim architecture. The input of the CoCoSim is a Simulink model attached with some properties to prove requirements. We will give a demo in the next chapter, and you will understand what is a contract and what is a property and how it's annotated with the model, how it is attached to the model. So once you have the Simulink model, you can simulate the model. You have all the constants in the MATLAB workspace. Then CoCoSim is doing all these steps presented in this slide automatically. First, it starts by pre-processing the model. Pre-processing is a very important step because it simplifies some blocks into another subset of more basic blocks to reduce the subset of the blocks that we need to translate to Lustre. The second step is internal representation engine, which is we will get all the information about the model and we will generate a hierarchical representation of the model in a JSON format, and we will save it in a file. So we don't need the model anymore. So the compiler can be developed in any language, Java or C++, since we have all the information about the model. And we can export it as a JSON format. That once we have this representation, you can generate, the third step is generate, it's a compiler or a translator from that representation to Lustre. Currently we support Lustre. It's a French synchronous data flow language, very famous in academia in model checking. But later on, we are hopefully looking to add other formal languages that support formal verification and support model checking. We choose Lustre because there are many model checkers that already support that language. Once you have the Lustre generated, you can do verification, you can do code generation, you can do test case generation because you have a formal representation of the model. you can do many stuff. So the pre-processing, I explained the pre-processing before. So it takes, like, for example, the saturation, and it substitutes the saturation block by a subset of blocks that do the same thing. For example, we can use the min and max block with the upper limit and lower limit, and try to saturate the inputs within the range of the upper bound and the upper. For example, the discrete transfer function, we can use the mathematical representation of the discrete transfer function and develop a similar subsystem that do the same thing, but using just the multiplication of matrices and the sum. So this like reduce the number of blocks that we need to translate to Lustre. So for example, here I give some blocks that we pre-process. The middle end, for the moment, we support Lustre and Prelude. We are looking to support SMV. Lustre is very similar to Simulink. It has it's a flattened textual language, but you have you have a lot of similarities. Like if you have a Simulink subsystem A, then we have a node A in Lustre, which is like a function. It could be stateful, like have memories or not. You have inputs and outputs similar to a subsystem in Simulink, and you have also, like for example, in this figure, we have the root model that has A, B, C subsystems, making the B inputs are the outputs of A and C. You can see similar to Lustre, you have a root node, and it's calling A and B, and then calling C with. And the order of equation in Lustre are not important because the compiler of Lustre is making sure that the order, it's synchronous data flow language, the order is computed at the compilation time. So it's very similar to Simulink. The advantage of using Lustre, so Simulink supports continuous time as well as discrete time, while Lustre is only supporting discrete time. For the moment, in CoCoSim, we only support discrete time Simulink models. Sometimes when we have a continuous block, like an integrator, we have a pre-processing that discretizes this integrator block into discrete integrator block. But we don't recommend that because the discretization is not it's not complete. You don't know exactly what is the step to discretize that integrator. So it's better to have the user do it and have a discrete version of the model and then run CoCoSim. So the advantage of Lustre as well, it has a unique precise semantics. It's well defined, and it's a strongly typed language. Where in Simulink we have some implicit typecasting, but CoCoSim takes care of that. It translates the Simulink model to Lustre, and it takes care of all the typecasting between data types and signals. Lustre is considered as a critical system language for SCADE. It's the textual equivalent language of SCADE, while Simulink was initially considered as a simulation tool, was not forcing a lot of things that are very important in critical systems. And also Simulink is evolving in time. A lot of things changed in the Simulink. Even the Simulink API or Simulink model, but hopefully with the way we develop CoCoSim is using Simulink APIs, and we don't use the textual representation of the model. We are not afraid that with some release of Simulink that can break the CoCoSim. That's what's happened with many tools that have been trying to verify Simulink models, and they are based on the textual language of the textual representation of the MDL file of Simulink. But we use the Simulink API because MathWorks will update the API, and we don't need to be worried about changing the Simulink file. What we support, the Simulink blocks, we support a wide range of blocks, like 100 blocks. That's the direct translation from Simulink to Lustre. But we support also other blocks in the pre-processing, like saturation to other blocks that we explained before. or discrete transfer function. So basically, I don't think that we have a problem in the limits of the blocks that are supported by Simulink. Most of the blocks that are used, even by NASA missions or by our industry customers, they hadn't have a problem with blocks that were not supported. If there is a block that is not supported, it will be abstracted for verification, but the user can also support it. The way the CoCoSim is developed is customizable, and the user can support blocks that we didn't support by himself or by herself. So no need for it's modular. The compiler is modular. Each block is supported by a class. The user can modify some translation of some block or add another support of another block. So modular code, that's what I was saying. And this compilation from Simulink to Lustre, it has been well tested, well validated. We have been testing this compiler very often to make sure that the translation is correct. We don't have a mean to prove the translation is correct, since the Simulink model is not formally defined, but we are doing our best effort to make sure that the translation is correct. So the backend parts of CoCoSim, once you have the Lustre, you can do mini stuff such as property checking using a model checker, or code generation, or test case generation. All these are supported by CoCoSim right now. The user doesn't need to know about kind2 and gkind and Lustre. Kind2 is only supported right now, but you don't need to know about what kind2 is doing, because we run kind2 and we bring the results back to the user. Here I just speak about how I validate CoCoSim. I don't think it's important for the user, but yeah. So how to install CoCoSim, we did it in the next video. You will in the next chapter you will see how to install CoCoSim menu. You will see it in the next chapter, and also requirements, how to attach the requirement to the model, and how to prove properties. So yeah, I think, do you have questions, Andreas, about the slides I presented?
Not really, no.
Okay, perfect. So this is just a high overview of CoCoSim. In the next video, we'll see how to install CoCoSim with even cloning the code using Git with whatever branch. Develop is the most recent branch. It's not stable. The master is more stable. Or you can download the releases from here. I explained how to do using one of the methods in the next video.